Hello and welcome to this Climate 201 episode from Physical Attraction. This episode, having talked about bioenergy with carbon capture and storage, we're going to focus specifically now on the carbon capture and storage component of it. So we've already discussed briefly CCS as a way of reducing emissions from fossil fuel power plants by capturing the CO2 before it's released into the atmosphere. And we've talked about how, when it's combined with biofuel power plants and under certain circumstances, it can be net negative and part of negative emissions, taking CO2 on average out of the atmosphere. Similarly, if you have other means of capturing CO2 from the atmosphere, you can then, at least in theory, use some of the same technology to store it underground. So we're talking about a three-step process. First is the actual capture of the CO2, then transportation, and then the permanent storage or sequestration of the CO2. Now for that initial capture, you have a couple of options. First is something called pre-combustion capture, where you would take the fuel, typically something like natural gas, and then heat it up in the presence of air, or oxygen, reforming it into hydrogen, which can then be burned by itself, and the CO2, which can then be separated out. So that's one thing you can do, but typically when people talk about CCS, they're referring to this post-combustion capture. So this is after you set fire to your fossil fuel, you catch the CO2 before too much of it gets into the atmosphere. The most commonly used method at present to actually capture CO2 is with a process called amine scrubbing. This is the dominant one that is used at present, although there are other ideas that have been proposed. What's used is a scrubbing material, for example, ethanolamine. This is a substance that reacts with and can absorb a molecule of CO2 when it passes by in a slightly exothermic and reversible reaction. So the scrubber saturates with CO2. Then you can heat it, which releases the CO2 molecule again, and you can therefore effectively catch some percentage of the molecules before they're released into the atmosphere by putting layers and layers of this material, or this material dissolved in solution, in the way of that flue gas. So there's a cycle here where you have the scrubber, it's exposed to the flue gas from burning fossil fuels which contain CO2, it absorbs the CO2 molecules, then you take it somewhere else, you heat it up, you release the CO2 molecules, preferably into some sort of container, and then those CO2 molecules can be compressed into a liquid, for example, and transported onto the next stop in the process, and the whole scrubbing process goes back round again. Now you can see from this already that there's going to be a sort of trade-off which broadly applies when you're selecting the materials for the scrubber here. Clearly, a substance that very tightly binds to CO2 molecules will be more efficient at plucking molecules out from the exhaust stream of the gases, but it may also require more energy to break those bonds again when you want to extract the CO2 from your scrubber for onward transportation and storage. For this reason, and for our classic thermodynamic reasons, which mean that none of these processes can ever be completely efficient, the process is not 100% efficient at capturing CO2. The best you can do is between 80 to 90% that's been realised in tests so far. Of course, the fact that you need to expend energy in the process of capturing and compressing the CO2 is another cost and another source of emissions if you're generating power through fossil fuels, for example. Optimistic estimates from the CCS industry suggest that this might boost the price of electricity generated with fossil CCS by around 40%. In the case of the CCS for industry, for industrial processes, depending on what you're making, for example chemicals, steel, cement, etc., the price changes will of course be different, but the basic point stands that cleaning up after yourself is still more expensive, and you still need a source of energy to allow you to liberate those CO2 molecules from your scrubber so it can be reused. And you'll need the same energy to transport and store the CO2 as well. So this is at least the theory of how CCS would work. How has it in fact worked in practice? For this, we can look to some of the pilot projects that have been taken up at the moment. There's about 23, 24 of them around the world at the moment, of which I think 2 are for power stations that are currently ongoing. And several more have been either commissioned and then not taken place, or been attempted and then shut down and so on. So when we're looking at some of these actual operational facilities, we can understand how this has been implemented so far. So one example is the Boundary Dam plant in Saskatchewan, in Canada, which is one of just 3 power plants that's currently fitted with a large-scale CCS. And when they launched this, they had a headline figure that said it would capture about 80% of the CO2 from the exhaust of its coal-fired power plant in the first few years of operation. Actually, the Boundary Dam plant, like many power plants, has several different modules in it, and this was only one of the modules was fitted with CCS. So most of the power plant is still just burning coal willy-nilly, but in this particular case, you've got one unit that was fitted with CCS, and they plan to capture 80% of the CO2 from that. Unfortunately, as with many of these pilot projects, which are halfway between a proof of concept and halfway between actually trying to do something, there are quite a few issues with this. So half of the CO2 that they captured was not permanently stored and was instead just released into the atmosphere again. Even the half that was actually captured was then sold to a company called Synovus Energy for use in, yeah, you guessed it, enhanced oil recovery, pumping the CO2 underground to help extract more oil. Now you can offset the cost of doing CCS a bit with that. They got about $20 per tonne for their CO2 to do this. But obviously it's not a large-scale, scalable solution that would actually reduce global emissions if you implemented it everywhere. There also appear to have been some pretty big engineering problems in actually getting the plant to perform as required and as expected. Equipment failures for the CCS retrofit on this plant meant that it's often been shut down. According to a 2014 report, a year or so after the original CCS plant opened, for large periods of its initial run, the CCS was switched off. It was perhaps only running around 40% of the time, although theoretically while it was running, it was operating at 90% efficiency while switched on. Things have improved a little bit in recent years, so their original goal was to capture 800,000 tonnes of CO2 annually from their operations. And it's now capturing 600,000, which is up from 400,000 compared to what they were doing before. But all of this is just to say that in practice, you are likely to get performance that is less good than the headline efficiency figures, and that's always the case regardless of what you're trying to build in the power sector and regardless of what you're trying to implement. So yes, with all the caveats about pilot projects having teething troubles and requiring extra development and scale-up and so on to work at cost, you might have a headline figure saying that it could be 90% efficient at capturing CO2. But when you dig beneath the hype, in reality, it's often operated at half that efficiency. Half the CO2 that they then capture is released back into the atmosphere, and then the CO2 that they do capture is sold straight back to the fossil fuel industry to enable them to extract more oil. So the green credentials of calling something like this clean coal are disputable, to say the best. And frankly, if all CCS plants are this bad at their job, and their job is seen to be mitigating CO2 emissions, it's hard to see that the industry is going to scale in a way that really reduces our emissions and helps tackle climate change at all. And remember, according to some of these models and these integrated assessment models, these economic models, we're supposed to have the carbon capture equivalent of a couple of thousand of these around the world that actually work by 2030, and 7,000 or 8,000 by 2050, at least according to the models. Now, they did receive a good deal of government funding for this project, but even then, the company behind this, having had a little bit of an experience and a taste of CCS, Sask Energy, they are retreating from what is now seen as a bit of an expensive boondoggle that hasn't really received any of the credentials that they wanted in terms of being green and clean, and hasn't been a bit of a nightmare for them to operate, and on the PR side as well. So they've abandoned plans to fit the rest of their coal-fired power plants with similar CCS retrofits. Instead, they're going to pivot to natural gas as coal starts to die out. So all of this did happen in 2014, 2015, this big boundary dam scandal. And you can find reports from the nascent CCS industry that is saying that they will now be able to deliver CCS cheaper, perhaps at 2/3 the cost of the boundary dam project. Now that may well be true, although of course it's worth saying that when you read the white papers from an industry itself, surprise, surprise, they're always kind of optimistic about how the industry is going to do, and they tend to come up with figures that look a little bit like the industry will be competitive with the alternatives and so on. And it would take far longer than I have here to go into that and try and work out whether their specific estimate is worthwhile or not. And perhaps it's not really that relevant, because this cost saving has yet to be demonstrated in practice. And even if it was at 2/3 the cost, you can still see that many of the fundamental issues with this are still in existence. So coming on to cost then, there are estimates all over the place in the literature for how much this might actually cost. A recent one by Hockman et al. And from the Royal Society proceedings suggests that if done in the US, you could capture and store CO2 from coal for around $60 a tonne and natural gas for around $80 a tonne. The difference there, of course, is that the coal emits more CO2 in the first place than natural gas. So to give you a rough scale here, if this could indeed be scaled up, emissions from the power sector in the US are around 1.6 billion tonnes a year. So for a mere 112 billion a year, you could do this for the whole electricity sector at least, although the most cost-effective path would obviously involve less CCS and more renewables and nuclear where it makes sense to do those things. It's also interesting to note that, as the Hockman paper points out, some of these cost estimates have actually increased over time, rather than going down. And this is due to the higher capital costs. The commodities that you need to actually build these big CCS plants in the first place, the pipelines and so on, things like oil, coal, steel, etc., they have become more expensive over time, and the cost of doing these infrastructure projects has become more expensive as other nations industrialise and compete for these assets and prices rise generally. The interesting thing about the Hockman study is that they sort of look at a regional application of carbon capture and storage. So specifically, they talk about the continental United States and how much CCS you could get deployed there. And in the context of that, you have some estimates that actually illustrate the different components of the cost in each case. So, for example, they estimate that the actual capture of emissions probably costs around $47 a tonne, about 3/4 of the total. Then the actual cost of storage. They propose to store the CO2 mostly by injecting it into land-based saline aquifers, or saltwater aquifers under rocks, and occasionally disused or old and depleted oil and gas fields where it makes sense to do that. Some people have also considered offshore storage in the past, i.e. under the deep ocean in rock formations there, but this is generally considered to be more expensive unless you already have some infrastructure there that can do some of the job for you, like an old oil well, for example. In the article, they estimate that the actual storage costs around $10 a tonne, but it could be anywhere between $5 and $20 a tonne. The idea is that you can transport most of the CO2 to nearby geological storage locations, particularly these saline aquifers. When you do it at sufficiently high volumes, like the sort of pipelines that transport liquid natural gas and oil around, it may cost a few dollars, perhaps $5 to $10 per tonne, to actually pump around a tonne of CO2 by about 250 kilometres. So if you have these big pipelines that are like the ones that the fossil fuel industry uses at the moment, then you have the ability to pump for about $5 to $10 a tonne, 250 kilometres. And those are the typical sort of distances you might be considering from your CCS power plant or industrial plant to a suitable location for permanently burying the CO2. So when we look at this, we can see that the cost breaks down about 3/4 for the initial capture, perhaps another eighth and a bit for the storage, and perhaps another eighth for the actual transportation. Why am I being so detailed here? Well, the point is to really dive into the breakdown of costs for CCS to persuade you that it might well be difficult to reduce this with some magical new innovation or new technology. Injecting the CO2 underground and pumping liquids around the place, these are both very mature technologies which have been used at scale by the fossil fuel industry for many decades. We know that the fossil fuel industry has been a multi-trillion-dollar industry during that time. They have got very good at pumping fluids about the place. It's unlikely that this is going to get much cheaper, because we're dealing with fundamentally physics here, right? We're dealing with thermodynamics. You can't invent a magic pump that's more efficient than the pumps that exist at the moment by an order of magnitude to make this thing much cheaper. We're talking about hard limits here, like the cost of actually laying the pipelines down, the energy that's required to push the fluids along it, and so forth. Now, it's true that injecting CO2 into rocks is a less mature technology than transporting it. But there are some good arguments to make that rather than getting cheaper over time, this could indeed get more expensive over time, because a lot of this cost is going to be dependent on the regulations that end up being put in place. If there's a lot of public concern around the potential for the CO2 to leak, or the environmental impact of this activity, this could increase the regulation, the amount of monitoring that you need to do, and it will probably require more stringent procedures and more concern for monitoring and evaluating the safety risks. It will probably also restrict some of the best sites that can be identified in a model from actually being used. It's very easy for all of us who do this sort of work to have our models of land spaces and say, okay, well, here would be a great place for a bioenergy crop, and here would be a great place for a wind farm, here's a great place for a solar farm, and we can put our pipeline here and inject our CO2 over there. But of course, in practice, actually, when you have these thousands of different icons on your GIS map of the world or whatever it is, and you're thinking these would be good sites for X, Y, and Z, the reality is you have to see who owns the land. You have to go there and see who's nearby, who might object, what the local law is for implementing these projects, like any infrastructure project. And I'm sure any of you who are listening who have ever been involved in this stuff will appreciate that there are many, many layers of administrative bureaucracy often to get through, and often for good reasons, but still it is in place that it's difficult to do these things because of the permits and so on that one requires. So the concern here is that for the CCS industry, that if there are public concerns about this being done at scale, it could be higher compliance costs for the industry as this is actually deployed in practice. And there's precedent for this because we've seen something similar with fracking for natural gas. Concerns about how fracking would be operating in terms of corrupting the water table or mini earthquakes and so on. This has just increased the regulations that surround fracking in order to keep people safe, and it has meant that the compliance costs for the fracking industry have gone up over time rather than down. And when it comes to that biggest component, the cost of capture, again, it's hard to see how you can make too many substantial savings. The energy requirements to add CCS to your power plant require at least 20% more input fuel in the first place. That component is going to depend on the cost of fossil fuels at any given time. But more dramatically, for most fossil fuel powered plants, it's not even just about this 20% more fuel you need to power the carbon capture side of things, but that it costs almost twice as much to build them with CCS as it does without, per kilowatt of generating power. The net result of this, the higher capital cost to build and the fact you have to use more fuel, this means that the end stage electricity you get out of generating with CCS is about 50% more expensive again, in most cases, in this levelised cost, compared to generation without CCS. A significant chunk of that is attributable to the extra cost of compression, transport and storage, and another chunk is attributable to that extra fuel you need to power the capture. But the largest chunk, over half, is down to the additional cost of constructing the plants in the first place. Put this then in the context of a world where renewables are already cheaper than fossil fuels across most of the world, and you can see that CCS would make fossil fuels even less competitive, which is why many fossil fuel power plants have resisted its application so much. Fossil fuels with CCS are closer to competing with nuclear power than they are renewables. For this reason, it's hard to see them playing a huge role in the electricity sector. But CCS itself may still need to be used for negative emissions and for sectors that are difficult to decarbonise, like industrial heat and steel production, where burning fossil fuels of some kind may well remain a cost-effective option compared to alternatives like hydrogen. Listeners to our series on nuclear fusion will remember some of the comments that we made there about how difficult it is to even get nuclear fission, a technology that has been around for decades now, off the ground economically anymore. And it comes down to some pretty fundamental aspects of project economics here, so let's just remind you of that. It's very difficult to get funding with projects with these huge initial capital costs in an increasingly financialised world where people are chasing quick profits. It's very simple, really. People don't want to give you $1 billion for a project that might start to make money in 5 years or 10 years, when they could give someone else a much smaller sum of money for a renewables project that can start generating and selling power in less than a year. As we said at the time, yes, your renewable projects might not be giving you baseload, it might be giving you intermittent electricity, but that's not going to be of concern to the investors unless they know that the baseload is going to get them paid a big premium for it. They don't care about anything like the makeup that the grid eventually has to have. And frankly, there's going to be a huge chunk of the grid that can be powered by intermittent renewables. And since that's going to be the cheapest stuff, that's going to be what people build first. Pretty obvious economics there. It's for this reason that most of the big capital-intensive nuclear fission projects require government investment or a government-guaranteed price of electricity to get off the ground at all. And we know that they're often subject to lengthy delays and overspend on their budgets. The UK is facing this now with many of our planned nuclear power plants cancelled or in jeopardy or at least delayed and overspending. And all of this is just as applicable to large-scale CCS projects. These projects only make sense at a very big scale. This means that the funding and the funding sources are very hard to come by. Again, it's not just the case that you're telling this financier, I can get your solar panels set up within 6 months, they can be built incredibly quickly and you'll start making money back straight away. It's not just the case that they need to put less money down and take less risk to begin with, and more people can finance these projects. The fact that it's so big scale to build a CCS plant makes experimentation and innovation more difficult. You can fabricate a new solar panel in a lab in a very short period of time, test it, innovate, make improvements in a matter of weeks. Now, it's true that you can do something similar for, say, an individual component of CCS, like the scrubber material, but for some large-scale CCS that's integrated with a power plant, these projects, the associated learning and development, they take years and huge amounts of funding to iterate and to make those technological improvements. This doesn't mean that you can't do it, but all of it makes it much, much harder to imagine the rapid scale-up and building of this type of project, which requires so much capital and engineering initially, such long lead times on the way in, and such a great deal of time and finance to succeed. And then, at the end of the day, once all of that is said and done, if it's guaranteed, have such an unclear path to being profitable in any kind of way. And all of this is from a fossil fuel industry that is increasingly struggling. We see this unconventional exploration and exploitation like fracking and so on, failing to recoup its costs in many cases. We see that US shale has been driven by this big debt-fueled bubble, while cheaper alternatives and climate policies both are impinging on the ability of the fossil fuel industry to make money as it once did. Rather than a long-term transition to a more sustainable model, as we talk about all the time here, most of these companies are planning for short-term exploitation, extraction and burning of as much fossil fuel as possible while they can still make a profit from it, rather than genuinely and honestly aiming for a transition to eventually running businesses where they can have a more expensive but cleaner form of utilising fossil fuels. So when you look at CCS, I understand that I talk about this all the time, but we have to get these technological silver bullet ideas out of our heads here. The fossil fuel industry can say it's going to invest in CCS as much as it wants, but given that it's something that currently makes its power more expensive and is a real faff to build, they won't do it unless they are made to. The only thing that will force fossil fuel companies to actually deploy CCS would be a mandate that makes them sequester some fraction of their emissions, or a carbon tax that's applied to everyone universally so that they won't be outcompeted by fossil fuel companies that can still choose not to use CCS. And as long as they can do this thing, where they are waiting for government regulation to force them into action, or they can say that it's the government's job to continue to develop CCS, or that the technology needs more testing and needs to be more mature, they're going to kick the can down the road, people. This is business, this is how it works. When you're in these businesses, when you're in these boardrooms, they're thinking, what's my profit for the next quarter? What's my profit for the 3 quarters after that? And that will always take precedent over what has to happen 5 or 10 years down the line. And so as long as they can keep procrastinating on doing this, they will. So, even if you are one of the people who is less against the fossil fuel industry, or at least its executives, than I am, and you believe that they can be a genuine, honest broker and a partner in the energy transition with a little help, you have to accept that their incentive structure is not set up for them to start deploying all of this stuff. And this again, it comes into the point that we make time and time again with these idealised economic models. It may well be true that it is the cheapest possible way to do things is going to be to deploy all of this CCS that the models predict. For everyone, right? Across the whole economy, if you average it across the whole economy, that might be the cheapest path to decarbonisation. But that doesn't mean it's going to happen, because the whole economy is not controlled by one person whose aim is to decarbonise the world, right? As it is in the model. There are many different players and actors in the economy. And from the perspective of the power plant companies, from the fossil fuel companies, they don't want to be the ones who bear the cost of action when they can benefit more from inaction. And they're the ones with their finger on the button and their hands on the lever and so on. And so this is why, although it may be the cheapest thing to do from a global perspective, when you look at the actual fact that there are individual players here whose incentive structures are all different, you can question how viable it is that this future is actually going to manifest itself. And if we don't have CCS at scale, then we need more renewables, we need more electrification, we need more demand-side management to actually achieve our climate goals. Sorry, you got me ranting again. I will get back to the main topic here, because something that you see a lot more of late is people trying to sweeten the pot of carbon capture and storage by describing this as carbon capture utilisation and storage. Of course, if you can find some use for liquid CO2, or indeed solid CO2, that allows you to create a market to sell it to someone, then you can offset some of the costs of capturing it rather than simply burying it as waste. But as we've discovered, the only thing that has made CCS projects so far viable tends to be a combination of big governmental subsidies and offsetting some of the cost by selling some of the CO2 for enhanced oil recovery. So currently, when you look at the global market for CO2, 88% is used for enhanced oil recovery, with around 6% in the food and drink industry, 2% for certain kinds of fabricated metals, and a number of niche applications. Clearly, if we're using CCS and utilising the CO2 to boost the production of fossil fuels, that's probably not going to be sustainable in a net zero world where our oil use will supposedly be minimal anyway. Now, some people have argued that it provides a useful on-ramp for CCS, allowing us to develop the technology, and it reduces the net CO2 impact of producing oil, at least as 90% of the CO2 that you inject underground to extract the oil does remain buried on a permanent basis. But part of the issue with this is that the fossil fuel companies view the CO2 and capturing it and using it in this way as an expense that they want to minimise. They're only going to push down the bare minimum of CO2 that's needed to push the oil out. So this is not being run as an efficient operation to bury CO2. Once again, we have different incentives here. There are a great deal of full life cycle assessments which try to determine whether the whole process is carbon negative or net carbon positive. There was an International Energy Agency estimate which suggests that using enhanced oil recovery to produce oil reduces the CO2 associated with that oil by 37%. Now, it's not clear, and it likely depends on a lot of details of the individual operation, but obviously it's not as efficient of disposing of CO2 than a process that is aiming to permanently bury it, right? It's just reducing the emissions associated with oil. And, if you live in a society where you can boost your oil production by 2/3 or something, then that will cancel out again. So the US Congress in 2018 passed the 45Q tax credit, which means that oil and gas companies get a $35 credit on their taxes for every tonne of CO2 that they bury this way. In fact, they get $50 for every other method of sequestration they use, but the enhanced oil recovery will obviously be the one that's favoured by this price structure. But of course, the disadvantage here, which I'm sure you can see, is that you are extracting oil that you wouldn't otherwise from a given well. You're therefore increasing the supply, which will lower the price and nurture our addiction to fossil fuels. So in turn, this can be a big problem. Currently, just 5% of US oil production uses enhanced oil recovery, injecting CO2 underground. But since EOR allows you to get at oil you couldn't obtain otherwise, squeezing out those last drops that are deep in the wells, perhaps as much as 80 billion extra barrels could be produced this way in the US overall. That would be another 10 years of the US's annual oil consumption today. And we really can't afford to maintain the consumption of oil at that level if we want to hit our climate targets. Projects for the unconventional extraction of oil from shale could provide even more oil in the long run. Furthermore, most EOR at the moment uses natural CO2 rather than captured CO2. At times, the amount of CO2, as well as exploiting the easier-to-access reserves, has prevented these problems from expanding. So it could genuinely be that a big CCS industry would provide enough CO2 to, ironically, maximise the ability of fossil fuel companies to produce more oil. The nightmare scenario for environmentalists here is that oil and gas companies get to pose as climate champions, they get the state to help fund them and subsidise the production of the CO2 that they actually need to exploit these unconventional reserves. I mean, if you look at it that way from a very cynical perspective for the prospect of this technology, it's kind of genius, isn't it, that they have sort of tricked the government into funding them to supposedly be green, but actually to extract more fossil fuels than ever before. And as a result of this, we wouldn't run out of oil to burn, and at best the whole process just slightly reduces the emissions associated with burning fossil fuels, rather than eliminating them entirely. So again, we're in a world of tension here when it comes to CCS. Do we have to work with the fossil fuel companies, who always have this incentive to extract, sell and burn fossil fuels and keep us hooked, frankly, to get to the future we want? Or do we instead need to work to eliminate them from the equation? And I wonder if some of this perhaps reminds those of you who listened to our last episode on biofuels of the dilemma there, right? Because you have one guy on one argument saying, well, wouldn't it be better if 10% of our fuel was biofuels? Then we would have cut down on the amount of total fuel that we were using and our CO2 emissions would fall by 30% or 5% or whatever. And then the other people would say, well, is it actually better in a world where 10% of our fuel comes from biofuels if we're still having this high penetration of the internal combustion engine? Do we just need to get rid of that entirely? So similarly, yes, emissions would be lower if all oil was recovered with EOR and there was some CO2 being buried as part of that process. But we would also still be dependent on oil, and ultimately we know we need to get to net zero we really can't be burning that much oil in the far-flung future in the next few decades if we are actually going to get to net zero. So there's a question as to how useful this sort of thing really is. And similarly, there's a question of the scale here. So I looked it up, and enhanced oil recovery currently accounts for about 70 million tonnes of CO2 being buried per year. And it currently also accounts for around 2% of global oil production. Returning to Glenn Peters' excellent analysis of different climate scenarios in the future across these economic models, you're seeing that median levels of CCS will be 10 billion tonnes of CO2 a year by 2050 for Paris-compatible trajectories. So even if EOR were to expand tenfold up to 2050, it would still only allow you to use 7% of the carbon that you're capturing in these scenarios. And we know that oil production will also have to fall in these scenarios to be compatible with 2 degrees Celsius. In the same scenarios, oil production shrinks by 20 to 30% by 2050. Even if we went totally unrealistic and suggested that all oil production would be done with EOR, then we'd still have a whole bunch of carbon that we wouldn't be able to use. And the International Energy Agency, their 2 degrees scenario foresees only around 500 million tonnes of CO2 being buried by EOR annually by 2050, which would be just 5% of that 10 gigatons that we're talking about overall. So whichever way you slice it, the most optimistic take here is that EOR could be a stepping stone for carbon capture to be developed more cheaply. But frankly, we can't use that much CO2. If CCS is going to take off in the way that it does in these scenarios, then it will only ever use a very small fraction of the total CO2 that we'd be burying each year, beyond the fact that it's problematic in other ways because it encourages the development of fossil fuels. So having slightly dismissed this prospect that we'll have some circular economy where CO2 is buried to extract more fossil fuels, our attention then turns to other types of utilisation. Is there anything else we could do in the future with billions of tonnes of CO2 that would be useful and that would offset the cost of sucking it out of the atmosphere? I mean, since carbonated beverages are around a 30th of the size of EOR, unless everyone really starts drinking a lot of Coca-Cola, that's not going to do it. So what else? Well, there is one idea that's often talked about, which is using CO2 to create a synthetic fuel. So, for example, let's say you have a direct air capture machine powered by renewables that is plucking CO2 out of the air. It sucks down CO2, which is processed into one of these synthetic fuels. In this process, you basically apply energy to the CO2, you break it down into carbon, you combine it with hydrogen to produce hydrocarbons, which are the basis for the fossil fuels we know and use today. The net emissions from this will clearly depend on how you get your energy, your CO2, and your hydrogen in the first place. The synthetic fuels produced could then be used in the hard-to-decarbonise sectors like aviation or shipping. Okay, so the net process is carbon neutral at best, because you then burn the fuel again. And of course it will be inefficient, so it probably will be net positive at producing some carbon, and would end up reducing emissions from these industries rather than reversing them or getting them to zero. And the fuel itself would probably be very expensive, and it would require a lot of renewable energy to produce. But this is one option for using the CO2 in a carbon neutral way, if not in any kind of permanent storage or sequestration way. But as it's really a cycling process, it only locks in the CO2 until the fuel is burned, so it doesn't quite fit the spirit of answering our question, which is what to do with the billions of tonnes of CO2 other than just bury it as waste. And for that reason, I think it's best to leave these technologies to one side and maybe come back to them later if there's interest from you guys. The one thing I would say here is that the major problem with these synthetic fuels at present is indeed the cost. So we're leaning here for this bit on utilisation on a huge literature review on CCUS that was conducted by a number of academics, which is called The Technological and Economic Prospects for CO2 Utilisation and Removal. And that was published in Nature a couple of years back. If you take a look at that, they suggest that as much as 4 billion tonnes of CO2 could potentially be used to make these synthetic fuels, which would be a significant chunk. Presumably at this stage, the synthetic fuels would be powering a great deal of aviation and shipping, but they also suggest that it would cost hundreds of dollars per tonne to convert them into the synthetic fuels. So that's a little bit more expensive than the other things that we've been talking about. Other uses for CO2 that have been mooted? Well, there are several companies and projects trying to find use for it as a building material. For example, mineralisation of CO2 converts CO2 into calcium carbonate, or limestone, which can then be used in certain kinds of concrete or asphalt. Concrete is basically a mix of water, cement, and aggregate materials. When concrete is mixed, the process of curing it generally uses water. You could substitute CO2 here instead of the water, which actually gives you stronger concrete. The process of making cement releases CO2. So there's an idea that perhaps this too could become a more cyclical process in the end. You would produce the cement, you'd capture the CO2 that is being made as a result of it, and then you would mineralise it for use in your concrete. You would end up with building materials in the form of concrete that permanently stored CO2, which could at the very least make carbon neutral concrete, depending on how efficient that process is and where you were getting the CO2 from, of course. It's true that humanity as a whole gets through a hell of a lot of concrete, perhaps as much as 10 billion tonnes a year, but obviously not much of that by mass would end up being sequestered CO2. The Nature review suggested that it might be possible to use anywhere from 100 to 1400 million tonnes of CO2 per year in these concrete building materials by 2050. So again, this could be a fraction of the total CO2 that would be captured, up to 1 to 14% if we really captured 10 gigatons a year by 2050. And it could potentially pay for itself in certain circumstances, although the cost estimates that they give, between minus $30, i.e. $30 of profit, and plus $70, i.e. $70 of cost, illustrates a lot of uncertainty for the value of actually using this CO2 into the form of CCS. It could be cheaper, at the high end of that, to bury the CO2 without trying to make it useful in the first place. Another prospect is chemical manufacture, and for the carbon that comes from plastics. This is a little dreamy, of course, but the point is that currently a good deal of our demand for fossil fuels essentially comes from the use we have in converting them into plastics and polymers. You can potentially imagine in the future that the main feedstock for them might come from the CO2 that we capture instead of fossil fuels, even through negative emissions perhaps. Although of course it's much more expensive to drag a few molecules of CO2 out of the atmosphere and convert them into a plastic than to do so directly from fossil fuels in the tried and honoured fashion. And the plastics indeed have their own environmental problems, as I'm sure everyone knows about. The chemical industry does use some CO2 already to make polycarbonates and urea in the production of ammonia. The Nature review suggests that this could find a use for between 300 and 600 million tonnes of CO2 a year at its maximum, although only a fraction of that would be permanently removed from circulation out of the atmosphere in long-lasting materials, and some of this would require a subsidy, i.e. you're not going to make any money from selling the products you've made from CO2, it's just going to offset some of the costs of doing that CO2 capture in the first place. So in some cases, again, it might be cheaper to bury it. Further afield, there are a few more interesting ideas. You can use highly concentrated CO2 to promote plant growth in greenhouses, where some fraction of it, at least, is used and stored by the plants. It's also been suggested that you could use it to promote the growth of algae. Now, algae have plenty of different uses. They can be converted into food, they can be converted into food for animals, they can be converted into biofuel feedstocks and so on. They can be used to make plastics and so on, but attempts to seriously commercialise algae have flagged in recent years. The Nature review talks about this potentially providing the use for another few hundred million tonnes of CO2, but again, processing the algae into useful stuff may cost a good deal, and as I say, various different attempts to commercialise this, including some famous ones sponsored by fossil fuel companies, have so far struggled to compete with the fossil fuel alternatives that exist. Another concept is to convert the CO2 into carbon nanotubes. There is a company that is currently doing this. We've talked in the show before, in episodes on energy efficiency, how these lightweight and strong carbon nanotube materials can provide an alternative to steel, but it's potentially all the cleaner if you can even source the carbon from carbon capture and storage. Carbon nanotubes potentially have all kinds of uses. They can even replace copper wires in electricity circuits, but the high cost of fabricating and manipulating them at present means that they are still really a niche application, and I suspect you would need quite a few more technological advancements to be able to produce them from CO2 in a cost-competitive way, even if they were being used for a lot of their different useful material purposes. In summary then, when it comes to carbon capture and utilisation, I'm trying not to be too much of a downer here. I certainly think that we should try to develop some kind of industries that make CO2 useful, and these are all interesting ideas. Particularly in the case of cement and concrete, this would help to decarbonise an industry that we know is a huge source of emissions and is going to be very difficult to decarbonise by other means. And so this particular process gives you a pleasingly short route to try to use the CO2 from its original source. Obviously, as much of this sort of thing as we can pursue, we certainly should, because it provides pathways for using materials that are carbon neutral, or sometimes even carbon negative to use, and we will still need those materials for our future. And it would be preferable to see CO2 being used for things like building materials or as algae food, rather than to nurture and enhance our dependence on fossil fuels in enhanced oil recovery. People like the Nature Review talk about this potentially being a multi-billion-dollar industry. If that's the case, then you'd hope that there would be plenty of investors who can make it work. But I also do suspect that in a lot of cases, it may simply wind up being cheaper and easier to bury the CO2 as a waste product rather than trying to use it. In particular, when we're talking about the vast quantities that we're considering in some of these models. There are not many things that we use billions and billions of tons of. Cement and concrete, we use 10 billion tons of that a year, which is on a scale of the CO2 that we use. And that's the second most used substance of all time in humanity, behind only water, apparently. So the idea that we'll suddenly find CO2, so many uses for it, that it will be the second most used substance of all time, I don't really know. There is certainly a kind of magical thinking to it. If we can find a use for the CO2, we'll be millionaires and it will drive us to do CCS and negative emissions because CO2 will suddenly be so valuable and there'll be a huge market for it and it will expand things using the free market, blah, 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 blah. So you can see the sort of free market libertarian point of view where this is a good idea, that you can clean up the earth and make massive amounts of money at the same time. And it sounds very appealing and attractive, at least in principle. But I simply don't think it will work out this way, given the amount of processing and energy you need to use to get the CO2 into a more useful form. There may be some cases, perhaps even up to 1 billion tonnes of CO2, where using that CO2 will help to offset the cost. But I don't think we can rely on it for much more than that. Even the most optimistic predictions out there for using CO2 can only muster that maybe around 10% of our current emissions could end up in some kind of useful product, or around 3 gigatons, compared to the 10 that we might capture in this median world with lots of CCS under Glenn Peters' model scenarios. I think it's probably optimistic that we'd even use that much, and the authors of this study do agree that you need a lot of strategic policy interventions to have a chance of getting there. And if all this CCS does materialise, to be honest, I expect that the stuff that's actually cost effective to use will only ever be a fraction of what's captured. Ultimately, I think we'll probably just have to face it. Sometimes you just have to clean up your mess, and it's not fun, and it's not profitable, but you just have to do it. Say it with me, people. New technology is not a silver bullet for our problem here. So, leaving aside the carbon dioxide we might actually be able to use for something, one thing that's regularly asked is, what are the risks from transporting and storing all this CO2, and where do you put it? Some of the good news is that the potential for leakage from the storage reservoirs is generally considered to be quite low once you actually get the CO2 there. This would obviously cause a big problem given that the idea is to permanently store CO2. If it leaks out over the course of decades or centuries, there could be long-term liability for the companies involved, and the monitoring of the storage sites would need to be paid for on a very long time horizon. However, this doesn't seem to be too likely at present. Even when it does leak from the intended original reservoir, secondary trapping of CO2 in higher layers of rock is likely to keep most of it underground. Researchers suggest that the amount that would actually leak from geological sequestration, simply by rising through the rocks, would be around 1% over the course of 1,000 years, so it's not a major concern. And if you combine the CO2 with saline brine, the saline water will sink deeper into the aquifer, as it's denser than the surrounding water, which should in turn aid sequestration. There are many other physical processes, such as mineralisation, where the CO2 gradually forms part of limestone and so on, which mean that over thousands of years the CO2 will become less likely to leak out. Even some worst-case modelling suggests that perhaps a third of the CO2 might be expected to leak out over 10,000 years, which is arguably not bad enough to make it not worth doing, particularly if you're a techno-optimist about the next 10,000 years. This is similar to the approach that has been used by a company called Carbfix in Iceland. So one of the things that they do is they inject CO2 into basalt-type rocks, and that reacts with those rocks to produce calcite, so it's mineralised and therefore more permanently stored. So this kind of geological sequestration is likely to be a lot less leaky than using abandoned oil wells. In the case of the abandoned oil wells and oil rigs, you have to be very careful to prevent blowout. The blowout of a full well is rare, but it can produce thousands of tons of leakage at once, so you have to be really careful if you're using millions of oil wells in the US, for example, as cheap storage sites. In other words, the prospect of slow leakage from the geological formations that the CO2 is injected into long-term is quite low, with some studies suggesting as much as 98% of the CO2 would remain in place for 10,000 years. Although, of course, it's tricky to know until you've actually done it and monitored it. Now, there would be safety concerns if there were major leaks from a pipeline, say, particularly in an enclosed area, so concentrated CO2 outgassing can indeed be lethal. There has been one such natural disaster already, where Lake Nyos in Cameroon erupted CO2, which killed over 1,700 people in the surrounding villages. it doesn't seem likely that anything like this would happen in a CCS pipeline unless there were some truly atrocious safety practices involved, given that the idea is to inject the CO2 hundreds of metres below the ground. But it is worth remembering that in high concentrations it can indeed be lethal. Like transporting any liquefied supercritical gas, you don't want sudden containment failures from something that is supposed to be kept at high pressure. It's hard to know until this is scaled up how stringent safety standards would have to be to prevent accidents, but the risk is generally considered to be pretty low and would probably only be a risk to people who are working directly on the pipeline. So then the question comes, how much CO2 could we actually bury, and where would we put it all? This is another one of those areas where we have to rely on technical potentials, how much we could technically deploy. But of course, the technical potential is always an upper bound to what can actually happen. I could probably argue that I have the technical potential to record 18 hours of podcast today, but that doesn't make it likely. At some point I'm going to want to knock off for lunch. Another issue, of course, is that what counts as viable storage depends on what you're willing to pay for the storage. So it's hard to come down to universal answers here. Much like the extraction of fossil fuels in the first place, some locations are better and cheaper than others, and the cheaper ones, as ever, are likely to be exploited first. However, at least according to technical potentials, it doesn't seem like the total amount of storage will be a problem. There are long-standing estimates that you could inject at least 920 gigatons of CO2 into depleted oil and gas fields, and perhaps over 10,000 gigatons of CO2 into deep saline reservoirs. Other estimates are even more optimistic, suggesting between 2,000 and 20,000 gigatons of potential storage could be stored in North America alone. So this would obviously correspond to many decades of our current global emissions, which are around 40 gigatons of CO2 annually, and that CCS of 10 gigatons a year that is the median figure from those 2 degrees Celsius scenarios, this is centuries of that. So it's much more than the scenarios project we would need. So as we've belaboured a lot here, the main barrier to this is actually scaling it and getting people to do it. But of course, there is a big difference between technical potential and sites that have actually been thoroughly assessed and are ready for use, which is a much, much smaller number, and the amount of CCS that is currently in planning and in the pipeline. So I remember seeing a presentation by a guy who was doing CCS, and he was talking about how there were thousands of potential sites that could be built in the North Sea, and that were supposedly going to be developed in the North Sea for Europe and the United Kingdom to do their CCS. But as yet, very few of them had been thoroughly explored, characterised, reserved. Construction certainly wasn't beginning on those, so he was very pessimistic about the rate at which these sites were being developed, and urged people, if this CCS was really going to take off, to get on with it. So in the round, what can we say about carbon capture and storage? Technically, it seems the technology for transporting and burying CO2 underground is indeed well understood. It's been used in enhanced oil recovery for decades. Pilot plants have injected millions of tons of CO2 into geological formations already over the last few years as part of demonstration projects, and demonstrated that it can indeed be done, and you can inject hundreds of thousands of tons of CO2 under the ground without too many ill effects in the places where it's done. However, at this stage, the high capital cost associated with CCS mean that it's really very difficult to see it playing a huge role in the power and electricity sector, where it has often seemed much more like a technology of prevarication. You have to remember that lots of these reports are being made in 2006, 2007, 2008. Since then, the price of renewables has plummeted so rapidly and to such an incredible degree that it seems extremely unlikely that these CCS power plants will ever be competitive. Even if the price of storage has to be factored in for the renewable power plants, it may well be that it just ends up being cheaper to do things that way than it will be to do fossil with CCS for the power sector. Huge issues remain with many of the actual projects that exist for CCS in the power sector, in terms of over-promising, under-delivering, going over budget, taking too long to construct, as well as selling the CO2 that they used for enhanced oil recovery, because there are no other major uses for it at scale. In the power sector then, it seems likely now that it will only ever play a niche role. And even this may not materialise unless it is mandated or a magical high global carbon tax is implemented, so that the industry actually has to be scaled. Because one thing we know for sure is that the fossil fuel industry is not going to develop this out of the kindness of its heart. Their incentive is always going to be to make short-term profits, and that doesn't involve doing something that makes their fundamental activity less profitable. If this was implemented, it would result in electricity from fossil fuels becoming less competitive compared to the alternatives. Now, carbon capture and storage does have more of a role, I think, in industrial processes like steel and cement manufacture, where it's very difficult to avoid CO2 emissions or the use of fossil fuels entirely in their production. We haven't yet developed really good ways of electrifying this incredibly high heat that you need for these things, And the fossil fuel use in industrial heat and in heating in general, it may well be the case that it's just easier and cheaper to use fossil fuels and go for CCS. And of course, if we need negative emissions at the end of the century, which looks increasingly likely, then bioenergy and direct air capture methods of negative emissions technologies will also need CCS to store it. So despite all of the caveats and flaws that we've mentioned, there are good arguments for still continuing to develop this technology. If we do conclude that we do require a negative emissions industry to scale up and reach our climate targets, then we should take some heart in the fact that the actual technology does exist and certainly works to an extent, with the cost as a core and key barrier to deployment. But even here, without mandates or taxes on emissions or something to make the industry do this, it is not going to develop itself by magic, because cleaning up your mess, ultimately, despite all of the many ideas for utilisation, is unlikely to be a profitable thing to do. One of the core points that Duncan McLaren, who we've talked about in earlier episodes of this series, made in his work is the idea that we need a separate target for negative emissions to ensure that they're actually developed, rather than just appealed to in modelling pathways or something that will show up in a few decades and never seen in reality. I think a similar set of mandatory targets for CCS is likely to be the only way that this industry is really going to be developed, rather than just bleating about how it's unfortunate but we do probably need some of it, blah, 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 blah. And hey, if you had these mandates, maybe people would change their minds about how important near-term emissions cuts are, or how feasible it is to develop this hypothetical industry in the future. Because if it's feasible to get 10 gigatons by 2050, then it should be feasible to get, say, 1 gigaton by 2040, and then it should be feasible to get 100 megatons by 2030, or whatever it is. And if they can't do that, then if the industry admits that it can't do that, then they have no viable way of scaling this up. And we can then finally say that CCS is not going to be the thing that is the decarboniser for many of these parts of industry. I don't think there's really much potential, in my view, for there to be game-changing cost reduction from coming up with better scrubbers beyond simply building the damn things out, because the basic principles are still the same old thermodynamics and chemistry that they've always been. Much like we've already seen with renewables, only learning through deployment will now reduce the cost of the technology. And we are running out of time due to the vast inertia in our energy systems, due to the urgency of the task at hand, to scale up this industry to the extent that is dreamed of in models. It is hard, when you think about this, not to look at the graphs of how people hoped CCS would be deployed 10, 20, 30 years ago, and compare those wonderful, exponentially increasing curves to the very flat line that represents the actual deployment that we've seen in those years, and then question whether CCS will ever really make it past this fledgling, failing pilot stage, and towards something that makes a substantial contribution to decarbonising our world and getting us towards a livable climate future. Thank you for listening to this episode of the Climate 201 series from Physical Attraction. You can find all of the episodes of the series, including every other episode that we've done too, on physicspodcast.com. There you will also find the contact form where any comments, questions or concerns can be addressed to me. I try and respond to all of the emails that I get. You can support the show in a number of different ways. It would be great if anyone is interested in climate change, if they want to learn more about the different technologies that can be used for you to send these episodes to them, send them along and tell them they can ask me any questions that they want to do. I want to really make this a good learning resource for people who are interested in learning more about climate change on the 201 side of things, getting a little bit more detail than the headlines that they see every day. And hopefully part of that is going to come from answering the questions that you guys have. You can, of course, also support the show on Patreon, where you'll have early access to all of the episodes that have been recorded so far, and some special bonus episodes that you can't obtain anywhere else. So please do sign up there on the patreon.com/physicalattraction. And thank you so much to those of you who have already done that. And if you don't want to do that, you can one-off donate to the show on the PayPal link that's also on the website at physicspodcast.com. You can engage with us on social media at physicspod. Maybe your suggestion is that I should write a script for this end bit rather than just trying to improvise it every single time. Whatever the suggestion is, please let me know. It's great to hear from you. Until next time then, thank you for listening, and please do, take care.